Hi, everybody. Welcome to PAW. It's my pleasure to introduce today Tess Anderson, who is going to speak on dyadic analysis, virtually meeting number theory because, Zoom. So Tess, go ahead.
Okay, thanks, Serena, and thanks for the invitation for the from all the organizers for inviting me to give this talk. So this talk is in the fields of analysis and number theory, but I'll try to make a very general style. So if you're a probabilist, it's a little more geared to our colloquium style. And in fact, I encourage lots of questions. The first time I gave this, I had a lot of graduate student attendees who asked a lot of questions, and that was fantastic. So please, whatever career stage you're at, feel free to interrupt. We're probably a few enough number that you can just unmute and ask. It will be a little easier for me to see than looking in the chat. So let me switch over to screen. Had it not focus as well. So I'll just write big. All right. So if you're paying attention, this is probably the part in the recording where we're going to start over when posting it to the website. So I will reintroduce the title of the talk, which is Dyadic Analysis Meets Number Theory. And since we're in a Zoom setting, this is sort of what happens. Is that dyadic analysis and number theory get together in a virtual room. And number theory comes on over and decides that we work really well together. And what happens? Number theory moseys on over and you get DNA. And the whole idea is that there is an intrinsic number theoretic structure in dyadic analysis. And dyadic analysis is a useful tool in harmonic analysis, but also related fields. If you're talking about martingales, or if you're talking about general dyadic decompositions and things like that, we'll mention several examples throughout the talk. So hopefully you'll be convinced that there's a lot of relevance of dyadic analysis in related problems and analysis in other fields. So what are we going to talk about that illustrates this DNA structure? Well, there's going to be two main themes. And as I mentioned earlier, we will probably only get to the first one, but I'll mention both of them. The first one is a complete classification of distinct dyadic systems, which I may also call adjacent dyadic systems. And I'll tell you what those are and how number theory comes into play. And we'll probably spend most of the time talking about that. But I'll mention the other theme, which is the potential failure, question mark, of what I term the Hasse principle in harmonic analysis. Now, the Hasse principle in general is something that comes from number theory and algebraic geometry. And basically it says if you have a variety, which is just a zero set of a polynomial, you can think of it as solution set for a system of equations, that if you have a solution mod p for every prime p, and you have some type of real solution, which indicates the prime at infinity, then that guarantees that you have, say, integer solutions. So it's a way to solve Diophantine equations by looking at them mod p. Now, there are many surfaces where the Hasse principle fails, and that's a deep and very interesting area of study in algebraic geometry. We're not getting that deep here, but we do introduce a variant of this principle in harmonic analysis and how it relates to doubling measures, which relates to a folkloric question dating back to the late 70s, early 80s. So there is definitely a number theoretic connection on this front. However, I probably won't get to talk to two, but point two you can read about in this paper on the archive, if I don't get there, called Dyadic Analysis Meets Number Theory. So the title of the talk is actually the title of the second paper. And that's with myself and Bing Yang Ho. Okay. But we're going to start with topic 1. And topic 1 is about the complete classification of dyadic systems. So let me tell you what a dyadic system is. First, we're going to start with the definition of a dyadic grid. Okay, so we'll do this very informally. Dyadic grid is a grid, which I haven't defined, so you know it's always bad practice to use the word in the definition in your definition, but I think you'll understand what I mean here. A grid on RD, so Euclidean space, satisfying 3 key properties. So I'm going to have to jump to page 2, leave you in meaningful suspense. Okay. So satisfying basic properties that we would like any nice structural breakdown of RD to have, namely that you can split it up into component pieces. We're going to call these cubes, where when you pick a set length, say 2 to the k, you completely tile the space. So the union of all the cubes is RD for k an integer. So k is an integer. Property 2 is that the intersection of cubes is one or the other, or the empty set. So you have this really nice intersection property. And the third one is a parent-child relationship. And if you think about the standard dyadic grid, or grids on spaces of homogeneous type, or even more general types of grids, they satisfy some variant of these principles. But we're looking here at natural extensions of the standard dyadic grid that you might have learned about in, say, an intro measure theory class in graduate school. So a parent-child relationship, what do I mean here? I mean that let's think about the real line. Every interval, which is a cube, divides up evenly into 2 children. And then each of those children subdivide into 2 more children. Each child has exactly 1 parent, etc. So it's a very nice, clean binary relationship. And the example that I keep on mentioning is the standard dyadic grid. And we'll call this D. And the standard dyadic grid consists of intervals at level 1 that look like -1, 0. So this is just on the real line here. 0, 1, 1, 2, etc. These are the level 1 cubes. You also have the bigger cubes, so intervals like 0, 2, 2, 4, etc. You have even bigger cubes, intervals like 0, 4, 4, 8, 0, 8, 0, 16, etc., etc. And then you have the small cubes, which look like 0, 1/2, 0, 1/4, etc. You'll notice there's something special about this point 0. It's always going to be endpoint of one of the cubes in your given level. So it's never going to be an interior point. And this will become very relevant shortly, because our next example will break this type of a property. So this is what's termed D1/3 on the real line. And I call this a 1/3 shifted grid, and it's best defined by drawing a picture. So here we have 0, we have 1/3. We're going to need 4/3 and 7/3. And then -2/3 and -5/3. All right. And for this type of dyadic grid, we're going to move our initial point from 0. So as you saw here, 0 is very special. It was always an endpoint of cubes. So we're going to move that special point to 1/3. So the cubes at level 1 will look like 1/3 to 4/3, 4/3 to 7/3, -2/3 to 1/3, etc., etc. And then that completely determines all the smaller cubes because you have the parent-child relationship. So you just divide up this interval on 2, etc. And you can do this for any subsequent generation. However, for the parent cubes, you're going to pick them a little differently than the standard grid. So let me just remind you that the small cubes, we're going to choose the usual parent-child division. And for the large cubes, we're going to choose the parents in an alternating fashion. So the parents are going to alternate. And what do I mean by that? I mean that we represent the choice of parents by choosing zeros if that cube is the right child of the parent that we choose, or ones if that cube is the left child. Okay, so we're going to start with our initial point 1/3. And for the first parent, we're going to choose like we would do with the standard grid. This interval here from 1/3 to 7/3 is going to be our parent interval. So in this case, this cube here that we're starting with is the left child. So we're going to write down a 0. Now at the grandparent generation, instead of choosing to start here and choose this parent like we would for the standard grid, we're instead going to start here at -5/3 and end at the same spot. So now we've chosen this cube here to be the right child of the parent. So we've alternated the choice of parents. So we would put a 0 then for the grandparent generation. For the next generation, we would go simply above here and extend to double the size for the next parent. And so you're going to get a sequence of 1s and 0s that are going to represent your parent choice. And this is how you define the 1/3 shifted grid.
Tess, can I ask real quick? So like this sequence is associated to, so every one of these intervals has the sequence associated to it.
Yeah, so this exactly. So it depends on what interval you're starting with on your level 1. So we're just going to assume to standardize this, that you're going to start with the interval that includes your initial point, wherever you want that to be. So if you pick an initial point and you pick a sequence, this will completely determine your grid.
Gotcha.
If you don't pick an initial point, yeah, there's a sequence that corresponds to every say level 1 cube, and it might be different. Like this one would be like a 0, because here you would start with being the right child instead of the left child if you were starting with this cube here. So you would have an alternation. So things would be slightly different with that cube there. So yeah, it very much depends on the initial point that you're starting with. Here we're doing everything around 1/3. And so you'll get this sequence and that will completely determine your grid, but you could start with another cube and your sequence would be slightly different depending on where you start. Yeah, so this will relate to later on when I'll tell you that you can use the initial point and the parent sequence to determine any grid that's going to satisfy these properties that we talked about. So these are defining features actually for determining your grid, which shouldn't be super surprising based on this example. But I don't think this concept had been explored so much until fairly recently, likely because this 1/3 grid already was very interesting. And this has been around for a while. So why is the 1/3 grid so interesting? Well, when you can combine it with the standard grid, D, you get that the two of them together form what's called a distinct dyadic system. And what do I mean by a distinct dyadic system? What I mean is that a distinct dyadic system is the minimal number of grids that you need to be able to have a really neat property. And that neat property is that any interval at all is contained in a cube of one of these grids of roughly the same size. So I'm going to make that really precise, but I'm going to mark this down here that there is a neat cube containment property that distinct dyadic systems satisfy. And that is, as I said, any interval at all is contained within a dyadic one of either grid of roughly the same size. So that enables you to compare cubes from your grids to just general intervals, no matter how big, no matter how small, whether they be dyadic or not, because you have this really nice size comparison property that's guaranteed once you have both D and D1/3. If you just have D, you don't have this. So let me make this precise. This property is usually termed May's lemma, named after Tao May, who did this first on the torus. And it says precisely, we'll write this down on the real line. And there are many variants of this, so this is just one of them. For any interval on the real line whatsoever, there is a cube in D union D1/3, such that your interval is contained in the cube and the length of the cube is not too much bigger than the length of the interval. Okay, so you're contained in a cube of roughly the same size. And this is often termed the 1/3 trick, or sometimes the 3-lattice lemma. That is, if you have D and D1/3 on the real line, you can always do this trick and you get this constant 6. There are other variants where you can use different constants, but this one isn't too difficult to prove on the real line. And indeed, as I said, there are many different generalizations of this and attempts to sharpen the constant and things like that. But for many applications, this is sufficient. I'll mention there's a monograph on the 1/3 trick and dyadic analysis in general by David Cruiser-Ribe. These notes appear on the archive. And this does a fantastic job of talking about the history of this trick and how it's often misquoted or misattributed. So oftentimes John Gornat or Mike Christ are quoted with this, but it's actually a bit older in the literature. So David Cruiser-Ribe sought out the primary sources for this and tries to detail quite carefully the history of this type of phenomenon. So one application of a lemma like this, or the fact that you have a distinct dyadic system, is the following. So let me write down application to show you why having a distinct dyadic system, besides this nice containment property, is relevant. So you have the dyadic version of the Hardy-Littlewood maximal function. And you can bound this above by the full Hardy-Littlewood maximal function. Because here you're just taking the supremum over more intervals. So this is obvious from the definition. But you can actually bound this above by a sum of the Hardy-Littlewood maximal functions on the dyadic grid and on the 1/3 shifted grid. And this is heavily reliant on this May's lemma. So essentially, it reduces many problems about the Hardy-Littlewood maximal function, such as bounding it, to bounding two dyadic versions, which is often much easier to do in practice. And for instance, this area in harmonic analysis that's typically termed sparse domination, it's related to this theorem that was proved in 2012 called the A2 theorem, heavily relies on this property. So basically every sparse domination paper at some point needs to use May's lemma to relate continuous objects to dyadic ones. So in general, whenever you have a lemma like this, you're able to relate continuous objects defined over any interval to dyadic versions. And moreover, what's important, a finite number of dyadic versions. And you can really even optimize the constants that you get in this. And so this leads to a large number of applications. So a natural question that might arise is, can we come up with more distinct dyadic systems? We know that D and D1/3 work. So can we find more distinct dyadic systems? And let's just focus on the real line. And one of the first papers to look at this more generally was a paper of Lee, Pfeiffer, and Ward. And they showed that 1/3, this magic number that appears on the grid, can be replaced by a number delta that is too far. And I'll define this shortly so you'll know what I mean by this, too far. So there's lots of different deltas that are too far, and any one of them will work. And then your D and your D delta, choosing the same type of parent in the alternating fashion will give you a distinct dyadic system. So now that we know that there's several of them out there, is that all of them? The answer is no. So the natural question is, can we actually classify all of them? So we know there are more than one. Can we, and like I said, I'll define what this is in a moment so you can see a little more clearly there's going to be more than one. So can we classify all of them? And so let's just focus on, again, on the real line. Can we classify all of them? And the answer is yes. And this is where my work comes in. And this started in my PhD thesis and then was revisited in many ways years later. So the first answer, yes, is on the real line. And that's in a paper with Bingyang Hu, and then a team of 3 undergraduates at the time, Jiang, Olson, and Wei, who are now all graduate students. And this paper just appeared in Math and Ellen in 2020, but you can also find it on the archive. And then the answer is also yes in RD, and this is a separate paper that I'll mention toward the end. And this one is just with Bingyang Hu, and it's submitted and you can find it on the archive. So, this dates back to about April of last year. And then if I have a little bit of time, I'll mention another relevant paper of myself and Bingyang Hu. Okay. So I promised an answer to, can we classify all of them? And I also told you I'd tell you what far is, and this is exactly where we're going to have the number theory show up. So let me define what the far number criterion means. So far numbers have the following definition. Delta in R is n far. And the reason I do n far, you can think of m being 2. This will relate to the dyadic case. Is in all the papers that I mentioned by myself and co-authors, we also consider distinct n-adic systems. So for instance, if instead of wanting to do things dyadically, you want to do things triadically or 5-adically, where each parent has 5 children, you can do that. So we consider all those cases as well. So we need this concept of n far, but again, feel free to just think of n being equal to 2. So delta is n far if and only if the difference between delta and points of the foreign k over n to the m is bounded below by a constant that only depends on delta normalized to the scale length. And this is for all m greater than or equal to 0 and k and z. Okay. And what does this mean? So these points here are the endpoints actually of the standard dyadic grid. So the endpoints of small cubes in the standard dyadic grid D. And so what it's saying is your number delta repels grid points normalized to the scale by a constant C delta. So of course, here we want C delta to be some constant bigger than 0. So it's completely independent of K, N, and M. So this constant, say, for instance, the case where delta is 1/3 and N equals 2, you can calculate the best constant. This is what I do in my PhD thesis, to be 1/3. And you can use some number theory to do this. So this case would mean that 1/3 repels dyadic points by this constant at every scale, no matter how small you go. So it's important to be able to do this for every small scale. This gives you an idea that this delta is going to be separated enough from the endpoints of cubes as to create a new and separate dyadic system. And this is really all you need to be able to do this maze lemma for the small cubes. However, this is only part of the story because we have the large cubes as well. So first of all, let me mention that in the paper that appeared Math and Nolan, we talk about the FAR numbers in some detail, and we have a lot of different classifications to determining if a number is FAR or not, but this one is probably the cleanest to write down. So delta is going to be N FAR. If and only if the sup, and I'll tell you what this is, of the length of ties is less than infinity. And let's just do base 2, so N equals 2. If I write out in binary my number delta, so I have some number delta, I'm going to write it out in binary. And let's say I get something like this. The tie is the length of consecutive zeros or consecutive ones. So this is a tie of length 4. And so it's just saying that you don't have an unbounded sequence of zeros or ones, or you don't have the bounds of those sequences tending to infinity. If you're looking at more general bases, you're only going to be considering the consecutive zeros or the consecutive digit n-1. So you don't need to worry about all the digits. It's just the digit 0 and the digit n-1. It just so happens that in base 2, these coincide. And so you're looking at all the possible digits. So if the sup of the ties is less than infinity, then you're a FAR number. This is closely related, but not quite the same to the concept of normal numbers, if you've seen that before. Okay. So I said this is only half of the story. The other half has to do with the large cubes, and as you might predict, has to do with the choice of parents. So one way to create a distinct dyadic system might come from changing your initial point, but this isn't enough. And so we're going to introduce the location function. And this is going to mimic what the choice of alternating parent did in the D1/3 case. So we're going to define a sequence A, A0, A1, A2, etc. Then we define the location function of A at point J, which is going to be the sum from L equals 0 to J minus 1 of A sub L n to the L. And the location function at 0 is going to be 0. So again, this might take a little bit to digest, but what this tells you is this is going to give the location of initial point of your grid, of your initial point, after choosing J ancestors. So the location function precisely tells you where your initial point ends up on the jth grandparent generation. So this will tell you all the information that you need about the large cubes, because you can do this for every generation. And then once you've determined your initial point where it goes to, then based on size requirements, it allows you to completely fill out the cubes of that level on your grid. So this location function will determine all your large cubes precisely. So then it shouldn't come as a complete surprise that with this information and with the examples that I gave, we can actually write any grid. So this is base n2, but let's just stick to the real line. And again, you can think dyadic base 2 as G with an initial point delta and a location function LA. This might not be a unique way of writing your grid. In fact, you can change your initial point and your, like Irina mentioned, and your initial point and your location function that will then likely change depending on how you change your initial point. But as soon as you have these criterion, you can completely determine your grid, again, non-uniquely, but still it's a way to completely determine any grid. And once you're armed with that, then you have the following theorem. So this is the paper with Bingyang Hu and Zhang Olsen and Wei. And it says that given two grids, G1, which is some G of delta 1 LA1, and G2, which is going to be some G of delta 2 LA2. So again, might not be unique. These are distinct. So again, the real line. So we just need two of them. And to be distinct, we need to satisfy these two criterion. It's actually an if and only if. So the first one is that the difference between delta 1 and delta 2 is n far. So if we think about the standard grid and the 1/3 grid, the number delta 1 would say be 0, and the number delta 2 would be 1/3. An absolute value, this is 1/3, which we know is too far because, well, I told you it was. You actually have to calculate that out. But again, I did some of these calculations in my thesis, and so these aren't too difficult to check with a little bit of number theory. The next condition is that you never have an extremal location, and that's measured by the following. That the lim inf in the difference of your location functions at point J properly normalized to the size of the cubes you're working with at those locations. Well, this is always going to be less than or equal to the lim sup of the difference of the location functions. Again, properly normalized to the size of the cubes you're working with, but this will never be 1. So your lim inf and your lim sup, your location functions will never differ by exactly n to the j. So if you normalize this, they will never completely differ by 0 or 1. They will never be extremal locations. So getting a 0 or getting a 1 is an extremal location. And it's okay to get a 0 or 1 as long as it's something that you get in the beginning, never get again. You never want to get a 0 or 1 infinitely often. So that's why we have the lim inf and the lim sup. You never want to infinitely often get these extremal locations. So I'll write that down here as in you never get. So never meaning not infinitely often, not ever. So in that sense, never get an extremal location. With these two conditions, you can determine that your grid G1 and your grid G2 form a distinct dyadic system. And so these are relatively not so bad to compute and practice. There's a lot of tricks for doing so scattered throughout this paper. And again, this is where a bunch of the number theory comes in, is relating the concept of distinct to this number theoretic property of being far. Now let's do our running example of D and D 1/3. We already said that 1/3 is too far. And we even have the constant. And then you can compute the lim inf and the lim sup, in this case exactly. Doesn't take that much work. The lim inf is going to be 1/3, and the lim sup is going to be 2/3. So these will never be 1 or 0, and so you're good. The proof of this theorem uses contradiction. So proof uses contradiction. But a nice feature is that it's not too bad to check these in practice if you want to work with a specific one. In addition to this theorem here, we have a uniformity of representation theorem, which basically says that even though your representation of your grids are non-unique, this type of condition is more or less unique. So let me actually write us on a new page. So unfortunately it's going to go away, but hopefully I can bring it back and remind you. So this is another theorem from the same paper, and this is a uniqueness theorem. So let's consider two representations for the same grid. So let's let G be some G1 of say delta 1 LA1, but also equal to some G1 prime of delta 1 prime LA1 prime. And then we're going to let G2 be the same thing with 2's. Okay, so you have two different representations for each of your grids. Then the theorem says that the lim inf and the lim sup parameters are either the same, no matter what representation you choose, or inverted. And what do I mean by inverted? I mean that if your lim inf is C1 and your lim sup is C2 for choosing whatever two representations you want to start with, then whenever you switch to another representation, you either get C1 or C2 again, or you get 1 minus C2 and 1 minus C1. There's only two possible choices. You either always get the same lim inf and lim sup, or they flip-flop in this sort of inverted way. So even though there's lots of different non-unique ways to represent the grid, if you want, you can play around with the standard grid and think of many, many different ways to represent it. I mean, you can change your initial point from 0, you can change it to 1, you can change it to 2. There's so many different ways. Your lim inf and your lim sup, when talking about, say, the standard grid with D1/3, will always be the same parameters, 1/3, 2/3. Now, in this case, when you invert 1/3 and 2/3 in this fashion, you still get 1/3 and 2/3. So in that case, it's very unique. But in the worst possible situation, there's only two types of cases you can get. So no matter what type of initial point you use to represent your standard grid and your D1/3, or what parent location function you choose, you will always get that lim inf and lim sup parameters to be 1/3 and 2/3. Okay. So now I'm going to spend the last 10 minutes or so just discussing what happens in the case RD. And this case is more difficult because you can't simply say, oh, let's do what we did on the real line and take a tensor product, as in, we know what this condition is on the real line. Now let's do this for R2 by considering cubes that are unions of D and D1/3, and you would then get 4 different dyadic systems. So if you were to think about this in terms of D and D1/3, you might think that on R2, for example, you could consider systems that are like D cross D, D cross D1/3, D1/3 cross D, and D1/3 cross D1/3 in this tensor product like fashion. And in fact, you can do this for certain applications, but the main issue here is that the sharp number, so the sharp or the optimal number of grids in a distinct dyadic system for RD is D plus 1, not 2 to the D. Okay. And this is not our result. This is a result of Jose Conde. So in certain applications, you might be able to get away with the 2 to the D grids, but that's not the sharp number. The sharp number is D plus 1. And so this throws a lot of wrinkles into the analysis. And in particular, how to analyze the geometry takes a step up in intricacy. And I'll show you just one example as to why that's the case. So we're going to look at the geometry. If you're looking on the real line and you look at endpoints of cubes and how they intersect, so these are the boundaries of your cubes. If you have a cube here and a cube here, basically the boundaries can only intersect in two ways. Either they don't intersect at all, and they intersect in the empty set, or they intersect at a single point. Okay. Maybe a maximum of 2 points. When you move on to R2, there's two distinct situations that already crop up. And this is just going up 1 in terms of your dimension. You could take 2 cubes here and look at how they intersect. Of course, you can still get intersection of the empty set, but you can get a situation like this where they intersect at 2 points here. Or you can get an intersection where they intersect at more than a point. Say they're intersecting here at a one-dimensional variety. Okay. This creates distinct situations to consider in the analysis. And very roughly what happens is if you project this down to the real line, these points of intersection are separated here. If you project this over, these points are separated over here. So we have the separation on both axes. With this case, you have the separation here on the y-axis, but when you project this boundary down, you don't. And so what this is going to mean is that a system that has this property will not be a distinct dyadic system, whereas systems that have this type of property will. And this type of geometric analysis, and there's an example worked out in a lot of detail with some fun colors in our preprint on the archive, so you can have a look there. But this example is really going to, in some ways, govern the types of distinct dyadic systems you can get. And in fact, when you do all the proofs, you can, in hindsight, come back to corollary. So again, you have to go through all the proofs to get here. But this does have a nice mirrored statement compared to the previous paper. So even though I said we couldn't just do this tensor product thing, we can do something that's somewhat equivalent, and that's this. The corollary says that G1 through GD plus 1 are distinct if and only if the projections of GI to and GJ to any coordinate axis are distinct in R. So at the end of everything, you do actually come back to looking at the real line case. So these grids are distinct if the projection of any two of them to any coordinate axis are distinct in R. So going back to this picture, a situation like this is good as we're projecting to the real line on both the X and the Y axis. A situation like this is bad. And so you do get this corollary, which has a clean statement in the end. We do get a theorem that mirrors very much the type of theorems that were mentioned before, but because of all the different dimensions and parameters in place, I think this is a slightly cleaner statement. Okay. And in the last, say, 2-3 minutes, I'll mention another paper. And so this is myself and Bingyang Hu. This other paper is also myself and Bingyang Hu. It's on the archive, and this is a different base case. So this was done maybe in September. And what the question we're considering here is, let's scoot this up, is what if you're going to mix different bases? So I said everything that we've done works for the dyadic case, but it also works for the triadic case, and it works for the 5-adic case, etc. So whatever base you want. But now if you want to ask the question, can I mix grids of different bases and get an adjacent dyadic system or a distinct dyadic system? That's also a very natural question to ask. And you might ask, in what cases can I do this? And so a sample question would be the following. So let's just take the standard dyadic grid D and any, no matter what shift you want, any parent choice you want. So any 5-adic grid. Can these be distinct on the real line? So no matter what initial point you have, no matter what location function you have, can you find a case where D and any 5-adic grid can be distinct? The answer is no. The bases to be distinct, the bases for all your grids have to be powers of the same number. Okay. So you can consider a 4-adic grid and a standard dyadic grid, but not a 5-adic grid. So they have to be powers of the same number. So even if you were to change this to something not co-prime, a 6-adic grid and your standard grid, you wouldn't be able to find any 6-adic grid that would make D and that grid distinct dyadic system. And there's an extension of this to RD as well. So this is true in R and RD. Okay. And this relies on developing the concept of far numbers to being far from a set. And then using a bunch of elementary number theory to essentially derive a contradiction actually on the small cubes. So it's likely there's also contradictions that arise on the large cubes, but we're actually going to just derive a contradiction on the small cubes. And I think I will end there and open it up to questions. Thank you.
Thank you, Tess, so much for the great talk.